Hello, ladies and gentlemen. I hope you're all doing well. Root Beer here, looking at question number 3 on the 2018 MMC paper. We've got two parts here, an A and a B. What is the sum of the digits of 10 to the 50 minus 5 to the 5? Okay, so 10 to the 50 seems scary, but it's very predictable. It's 1 followed by 50 zeros. Okay, this number is huge. And 5 to the 5 is something like 3,125. It's very, very tiny. Big number, and then just a little bit there at the end. So imagine 1, a whole bunch of zeros, and then the last 4 you're subtracting something from. I'm gonna say we're gonna get a bunch of 9s, and then the end bit is a little unpredictable. So what we're gonna do is we're going to experiment a little bit. Okay, that's what we're gonna do. We're gonna get some number of 9s. The question is how many. So how about we take a look at something like 10 to the 6, because I know 5 to the 5 is 3,125. If I didn't, I can easily calculate that out. Just 5 times 5 is 25. 25 times 25 is 5 to the 4, and that's 625 times another 5. All this can be done by hand. So what happens when it's 10 to the 6? Well, we line our numbers up. We're just going to subtract old school. So we need to borrow a bunch of 9s. We got a 5, a 2, an 8, a 6, and then the 9s. Okay, how about 10 to the 7? It's going to look very similar. So cancel all of those, turn into 9s because we keep borrowing and borrowing and borrowing. There we go. 5, a 7, an 8, a 6, and now 3 9s. So with 7 we got 3 9s, with 6 we had 2 9s. So I might say something by pattern recognition. I mean, you should be writing up all your responses, but you don't have to be super, super rigorous, especially for something like question number 3. So 10 to the n minus 5 to the 5. For any n bigger than or equal to 5, really. It's going to equal n, or 9, 9, 9, 9, 9, 9, and then 6, 8, 7, 5. And what are we going to have here? We're going to have n minus 4 9s. So the sum of the digits we're going to have n minus 4 9s plus a 6, what was it, a 6, 8, and a 7, and a 5. So this is 9n minus 36 plus 6 and 5 is 11, and then 8 and 7 is 15, so plus 26. So this is going to be 9n minus 10. And now I can do the question for any number, but specifically for n equal to 50, we're going to get 9 times 50 minus 10, and that's going to be 450 minus 10. Sum of the digits is 440. And that's all there is to it. Okay? So, nothing else I really want to say about A part. Let's get on to B part. Evaluate the sum f1, f2, f plus f3, all the way up to f100, where f of k is equal to 1 over 4k squared minus 1. Now, this question, it's not as weird as it might seem. There's actually sort of a very useful to know for more upper year, sort of university level or just before university level contests, where you can get questions like this. This is going to involve what's called a telescoping sum. Now, I can see that right off the bat. That's largely because I teach a lot of first-year calculus, just a lot of first-year calculus. But let's ignore that. Let's ignore any instinct we might have for a telescoping sequence. Let's discover this one together, okay? Just in case you haven't seen this one before, or anything like it. So, okay, we have to do all the way up to 100. Now, just like the first part, let's do some pattern recognition. Let's just look at F1, F2, and F3. And we've got 1 over, what is it? It's 4k squared, so 4 1 squared minus 1, so that'll be a third well, let's actually write it out for our first time. 4 minus 1, and then plus 1 over 4 times 2 squared, 16 minus 1. Plus 4 times 3 squared, so 36 minus 1. So that's 1 over 3 plus 1 over 5 plus 15 plus 1 over 35. Okay, well, we could get a common denominator here. Let's do that. So common denominator of 105, you'll get 21, not 21, 35. 35 over 105 plus 7 over 105 plus 3 over 105. And there we go. And that's going to end up being 45 over 105. And then you can divide by 5. You'll get 9 over 21 here. Okay, so 9 over 21 is our answer. All right. Before moving on, let's look at just some smaller ones. 1 over 3 plus 1 over 15. Well, that's the same as 5 plus 1 over 15. 6 over 15, and that's going to be 2 over 5. So 2 over 5, then 9 over 21. Okay, and then, well, if we just had 1 over 3 by itself, maybe we were just doing F1. We had to add all the way up to, from F1 up to F1. We'd have 1/3, 2/5, 9/21, and maybe we're not seeing a pattern. Maybe we're not seeing a pattern. That's okay. But we could explore a little bit more. 1 over 4 plus 1, 1 over 16 minus 1. I said plus 1 first. I didn't mean that. 1 over 36 minus 1. 1 over, what would the next one be? It'd be 64 minus 1. And we're starting to get lots of numbers. Okay, 1/3 plus 1 over 15, 1 over 35. There's got to be some sort of a better way to do this. Because what's the common denominator I'm going to have now? 945. Actually, no, 945, because 63 does have a factor of 9. Okay, so there's going to be a lot going on here. Okay, so we could have 315 over 945 plus need an extra 3 and a 7, so 21 over 945. Need 2, so we need a 9, so 945. And then we'll have a 3 over 945. Okay. And if you think, well, this is taking me a long time, and I'm having to figure out these common denominators, and these numbers are just getting bigger and bigger and bigger, you're not alone. Okay, you are not alone. But it'll turn out in just a moment that there's another way to look at this by focusing on the denominator. But let's try and finish this off. Do I really have a multiple of 3 each time? No, this shouldn't be a 3 at the end. This should be a 5. And it should be 315. Yeah, 945. I had it wrong. Multiply by 5 top and bottom, you're going to get 315. So I need 315 here, 315 here, 315 here. Okay, I was wondering why the numbers were so much lower than they needed to be. This will be 105. There we go. So 110 plus 30, so that's 140 over 315. I can divide by 5 on top and bottom, so that's 28 over 63. I can divide by 7, and that'll end up being 4 out of 9. Okay. Oh, this 9 over 21, by the way, should have been 3 over 7. Ah, and there are patterns a bit more apparent. 1 over 3, 2 over 5, 3 over 4. Odd numbers on the bottom. And then that odd number minus 1 divided by 2 on top. Okay? So that might be the general pattern you notice. Now, how is that going to help? Well, we could just jump to the end. You know, where does the 9 come from? Where does the 7, the 5, and the 3, and how can we generalize the pattern? But there's something a bit more interesting going on here. 1 over 4k squared minus 1 is 1 over k, 2k plus 1, 2k minus 1. And this can actually be broken up into a difference of, it's not quite these numbers. What is it? It's 1/2 2 over 2k plus 1, 2k minus 1. So it's 1/2. How can I write 2? I can write 2k plus 1 minus 2k minus 1. All over 2k plus 1, 2k minus 1. And now I can break this up into 1/2 1 over 2k minus 1 minus 1 over 2k plus 1. So now when I do this, f1 plus f3 plus f5 plus, and it just keeps going. Oh, not f1, f1, f2, f3. My brain's quite scatterbrained for just question 3. I might have to take a break before we do question number 5. Not that you'll notice, because I'll just post those 2 videos together. But we're going to have 1/2 of 1 over 1 minus 1 over 3. And that was f1. 1/2 of 1 over 1 minus 1 over 3. Well, that's 1/2 of 2/3, and that is 1/3. And that is what we get just with f1. But f2 is 1 plus 1/3 minus 1/5. And then we get plus 1/7 minus, plus 1/5 minus 1/7. And then we go plus 1/7 minus 1/9. Each one of these contributing in its own way, and we half everything in the end. So f100 here would end up being plus 1 over 200 minus 1, so 199, minus 1 over 200 plus 1, so 201. And what happens here is part of the previous term cancels out with part of our current term. So minus 1/3 plus 1/3 cancel out, minus 1/5 plus 1/5 cancel out, minus 1/7 plus 1/7. It all cancels down the line until you're left with just 1/2 of this 1, who doesn't cancel with anything, and this minus 1 over 201, which doesn't have the next term to cancel out with. Okay, so this is what we would end up getting. This is called a telescoping telescoping series, when part of the previous terms cancel out with some of the later parts of the later terms. So we get 1/2 201 over 201 minus 1 over 201, and we'll get 1/2 200 over 201, and so our final answer is going to be 100 over 201. Now, if you recognize the telescoping series, which you might if you do any math enrichment programs, I know I learned about telescoping series in about grade 11 or somewhere about that. So if you recognize how to do telescoping series, this is a great way to do it. But if you don't, of course, just writing out these first few terms and remembering, of course, to simplify, because I didn't have that simplified. 1 over 3, 2 over 5, 3 over 7. You can tell it's going up by odd numbers. Okay, and this would be if we added up to all the way to f4. Well, how do I get 9 from 4? You double it and add 1. And so your n goes on top, and that's exactly what's happening. We added up to 3 here. It'd be n over 2n plus 1, and that's the answer. Now, that's not the biggest proof ever. That's just pattern recognition. But this right here, all this stuff, is a real proof, a real technique that you can use, and will likely come back in sort of a late first-year calculus course you might take. So it's a nifty thing to look at. But either way, our answer for 3B is going to be 100 over 201. 2 different ways to go about it: pattern recognition or telescoping series. They are fun to play around with. But the time for that is over. We're going to move on to question number 4. I will see you for that next time.